Hello guys, welcome back to my channel. I know it has been a long time, but I'm back to posting again. So if you're new here on this channel, I'll be doing IGCSE physics related content. So I'll be doing past paper, topic questions, and overall revision. So for today, I will be going through the topic of electricity. So I'll be going through the different kinds of questions they bring up and how to solve the different kinds of questions. So after watching this video, you'll be able to solve all the types of electricity questions that bring up. And it's important to know how to solve this question because these questions could come up a lot. So it's very important you know how to do each and every one of them to get a good grade. So let's start with the first question. Figure 9.1 shows a 12-volt battery connected in a circuit containing resistors A, B, C, and D. Each resistor has a resistance of 6 ohms. Calculate the combined resistance of A and B. So A and B, they're both 6 ohms, and also they're in series. So what we do is we just add the resistance. So it's going to be 12. 6 plus 6 is going to be 12 ohms. Part 2. Resistors A, B, and C. So now this C is also 6 ohms. So what we can do is we have 12 ohms over here because we know their total is going to be 12. So now these two resistors like A, B, and C, they are in parallel. So what we do is we do R1 times R2 over R1 plus R2. So when we do that, we can do 12 times 6 over 12 plus 6. So this would give us 72 over 18. So that would be 4. So it's going to be 4 ohms. Part 3. Resistors A, B, C, and D. So now the resistance of this total unit is 4 ohms. And then we have this which is 6 ohms. So this is in series. They're connected in series, so we just have to add them. So 4 plus 6, that would give us 10. So answer is going to be 10 ohms. Let's move on to B. Calculate the current in the battery. So we know the formula for current, which is going to be I equals to V over R. So this formula is derived from the formula V is equals to IR. When we rearrange this formula, we can get I equals to V over R. So voltage from the previous question is 12 volts over here. So it's going to be 12, and the total resistance as we have calculated is going to be 10. So the answer is going to be 1.2 amps. Part 2. The energy transferred from the battery to the circuit in 50 seconds. So the formula for the energy transferred is going to be E is equals to current times voltage times time. So the current is 1.2 times 12 times 50 seconds. So that would give us 720 joules. Don't forget to write the units. Let's move on to question 2. Figure 8.1 shows 3 lamps and a fuse connected to a power supply. The AMF of the supply is 220 volts, as shown over here. Each lamp is labeled 220 volts and 40 watts. The rating of the fuse is 2 amps. Calculate the current in each lamp. So to find the current, we can use the power formula. So power is equals to IV. So we know that each lamp is labeled 220 volts and 40 watts. So it's going to be 40. Sorry about that. 40 watts is going to be equals to the I, which we don't know, times 220. So we can just divide both sides by 220, and in that way we would get the current to be 0.18 amps. Part 2. Calculate the current in the fuse. So to find the current in the fuse, when we go back to the diagram, we can see that the lamps are in parallel, so the current is going to be shared, but after that, once the current has passed through, all the current from the three lamps would come back into the fuse. So the current in the fuse is the sum of all the current in the three lamps. So what we can do is, since they are identical lamps, we can do 0.18 times 3, since we have three lamps, which would give us 0.54 amps. 0.54 amps. That's going to be our answer. Part 3. The total number of lamps all in parallel that could be connected without blowing the fuse. So from the question, they've told us the fuse has a rating of 2 amps. So that means it can take a maximum of 2 amps. So if each lamp has a current of 0.818 amps, so we can do 2 divided by 0.18. So this would give us 11.1. So the number of lamps that will be connected is going to be 11 lamps. That's the maximum number of lamps. Let's move to part B. After a very long period of use, the wire filament of one of the lamps becomes thinner. Underline the effect of this change on the resistance of the filament. So this is going to be, resistance is going to increase, because if the wire becomes thinner, that means the cross-sectional area is going to be smaller, so less electrons would be able to pass. So let's say the wire was this thick at first, so more electrons could pass at once, but then when the wire became thinner, that means less electrons would be able to pass, so that means resistance increases. Part 2. State and explain the effect of this change on the power of the lamp. So the power decreases. This is because from the power formula we know that power equals to VI. So in this case, since the resistance has increased, the I also decreases. So the power decreases due to the decrease in current. Decrease in current. That's going to be our answer. Let's move on to the next question. The circuits of figure 7.1 includes an immersion heater and a 6-volt battery. State the name and purpose of component X. So component X is a variable resistor. So the name is a variable resistor, and its purpose is to change the current. Part B. The heater is designed to work from a 3.6 volt supply. It has a power rating of 4.5 watts at this voltage. By considering the current in the heater, calculate the resistance of component X when there is the correct potential difference across the heater. Now this is a 5 marks question, so it's a big one. So for this question, we need to consider the voltage of the heater and the power. So first we can find the current in the power by using the current inside the heater by using the power formula. So we know that power is equals to VI. Rearranging this, we get I equals to P over V. So P is 4.5 over 3.6. That would give us 1.25. So this is the current inside the heater. And now on the question, they have given us the cells have 6 volts of power, and the heater only consumes 3.6 volts. So that means the remaining is going to be 6 minus 3.6. The remaining is going to be 6 minus 3.6, which is going to be 2.4 volts. So after the heater have used 3.6 volts, the remaining is going to be 2.4 volts. And then after that, we can find the resistance. So we know from Ohm's law, V is equals to IR, and then divide both sides by I. Resistance is equals to V over I. So we can use this formula. So the remaining voltage is going to be 2.4. And then the current in the heater is going to be 1.25. Now this is a series circuit, so that means the current is going to be the same everywhere. So the current in the variable resistor is also going to be 1.25. So that means we do 2.4 volts over 1.25 to find the resistance in ohms, and that would give us 1.92 ohms. So that's how you get the 5 marks. C. Sometime after the heater is switched on, the ammeter reading is seen to have decreased. Suggest why this happens. So this is because the battery will be drained. It will be drained. So that means there's less EMF. So less EMF from the battery, which would decrease the current. So because of this, the current decreases. So current decreases. That's going to be our answer. Question number 4. In figure 9.1, a 12-volt battery supplies a current I to a circuit. The circuit contains a thermistor and a 1000 ohm resistor in parallel with a 500 ohm resistor in series. So this is a thermistor, and then we have 1000 ohm in parallel to the thermistor and 500 ohm resistor in series. At a certain temperature, the thermistor has a resistance of 1000. Calculate the combined resistance of the thermistor and the 1000 ohm resistor. So they are in parallel. So at this point, the resistance is going to be 1000 for the thermistor. So what we can do is R1 times R2 over R1 plus R2. That's the formula when resistors are in parallel. So it's going to be 1000 times 1000 over 1000 times plus 1000, that's like 2000. So we can cancel out the 2 zeros. So 1000 over 2, that's going to be 500 ohms. That's our answer. Part 2, the current I. So to find the current, we can use the formula V equals IR, and then divide both sides by R. So I is equals to V over R. So the voltage is going to be 12. Now the resistance. So the resistance over here is going to be 500 ohms. Now since it's in series with the 500 ohms, we can just add them, giving us 1000 ohms of resistance. That's a total resistance in the circuit. So we can do 12 over 1000, which is the total resistance. So we can do, that's going to be 0.012 amps. That's the current inside the circuit. Now the potential difference across the 500 ohms resistor. To find that, we use the same formula, V equals IR. So the I is going to be 500 because we're asked the voltage across the 500 ohms resistor. And this is a series circuit, so that means the voltage varies across the circuit. And then the current is the same across a series circuit, so we just use 0.012. And when we multiply that, we get 6 volts. That's our potential difference. Part B, the temperature of the thermistor is increased so that its resistance decreases. State the effect of this change in resistance on the current through the 500 ohm resistor. Explain your answer. So if the resistance decreases inside the thermistor, that means there's going to be more current. So that means current increases across the whole circuit. And because of this, the total resistance is going to decrease. So the total resistance will decrease. This is because current and resistance are inversely proportional. If one increases, the other decreases. So in this case, the current increases, so resistance decreases. Let's move on to the next one. In the circuit shown, figure 9.1, resistors can be connected between terminals P and Q. The EMF of the battery is 6 volts. Calculate the current shown by the ammeter when a 12 ohms resistor and a 4 ohm resistor are connected in series between P and Q. Since these resistors are connected in series, that means the total resistance is going to be 12 plus 4, which would give 16 ohms, and current is equals to V over R, so that means it's going to be 6 volts over 16. So 6 over 16 would give us 0.375. We can round it as to 0.38 amps. That's going to be our answer. Part 2. Connected in parallel between P and Q. So if they are connected in parallel, that means to find the total resistance, we're going to have to do R1 times R2 over R1 plus R2. So it's going to be 12 times 4 over 12 plus 4. So this would give us, so 12 plus 4, that's 16. Sorry about the mistake. 48. So this would give us 3 ohms. So we still have to use the same formula, I equals to V over R. So that would give us 6 over 3, which is 2 amps. Part B. State the relationship between resistance R and length L of a wire of constant cross-sectional area. So the resistance is directly proportional to the length. So as the resistance increases, the length decreases. So we can write as R increases, L decreases. Also, okay, L increases. Part 2. The resistance R and the cross-sectional area of a wire of constant length. So the relationship is inversely proportional. So that means we're going to have R is proportional to 1 over A. So as A increases, R would decrease. As I have explained this before, so if you have a thicker wire, that means more electrons can pass through, so resistance decreases as the current increases. But if we have a thinner wire, less electrons would flow, so that means resistance is going to increase. Part C. The 12 ohm and 4 ohm resistors in A are wires of the same length and are made of the same alloy. Calculate the ratio of cross-sectional area of 12 ohm resistor and cross-sectional area of the 4 ohm resistor. Now we gotta be careful here because it has asked us the ratio of the cross-sectional area, not the ratio of the resistance. So that means since we know that resistance is equals to 1 over the area, so what we can do is we can flip the two values. So over here it's the 12 ohm over the 4 ohm one. So what we can do is we can flip them and it would become 4 over 12. Now this is not the resistance, it's the cross-sectional area. So this is 4 is the cross-sectional area for the 12 ohm resistor. So since 12 ohm is bigger than 4 ohms, that means the cross-sectional area is smaller for the 12 ohm, and 12 is the cross-sectional area for the 4 ohm resistor. So this is for the 4 ohm, this is for the 12 ohm. So as you can see here, 12 is a big cross-sectional area, so that means the resistance decreases. So the ratio is going to be 4 over 12, but we can simplify it to become 1 over 3. So we can write 1 over 3. That's going to be the ratio. Next question. Figure 8.1 shows 3 cells, each with EMF of 1.5 volts connected in series. Calculate the combined EMF of the cell. Okay, this is a simple one. We just add 1.5 plus 1.5 plus 1.5. As we have 3 cells of 1.5 volts, that would give us 4.5 volts. B. Calculate the combined resistance of the 3 resistors shown. So we would do the same step. So first we combine these two. So we can add 4 ohms plus 1 ohm, which would give us 5 ohm. So now we have this 5 ohm, which is parallel to the 1 ohm resistor. So we use the parallel formula. So R1 times R2 over R1 plus R2. So that would give us 5 times 1 over 5 plus 1. So this is actually 5 over 6. That would give us 0.83 ohms. Calculate the current in the 4 ohm resistor in figure 8.1. So the current in the 4 ohm resistor, this one over here. So to solve this question, we would use the formula current is equals to V over R, but be careful to use the total current and also the total resistance in series. So that the total voltage is going to be 4.5 volts, and we will use the resistance, which is 5 ohms, since these two are the ones in series, and current in a series circuit is the same. So we do over 5. So it's going to be 4.5 over 5, which would give us 0.9. So our answer is going to be 0.9 amps. D. Calculate the combined EMF of the cells if one cell is reversed. So we know that each is 1.5. Since one of them is reversed, we can add the first two, but then subtract the last one. So it's going to be 1.5 plus 1.5 minus 1.5, which would give us 1.5 volts. Let's move on to the next one. Figure 8.1 shows 2 resistors X and Y in series. Complete the table below using only the symbols I, R alone or in combination. So for resistor X, resistance is R. current is I, and the potential difference, that's going to be IR. For Y, the resistance is 2I, and the current is still I, because current in a series stays the same. And the power, so the power is going to be IV. So if the power is IV, that means that V is also equals to IR, so it's going to be I times R. But then the R over here is 2R, so we're going to have 2R. So that means it's going to be I squared R times 2. That's going to be our answer. Part B. Figure 8.2 represents the system used to transmit electricity from a power station to a factory. So we have 11,000 volts in the power station, and then we have 750 amps. The power station generates 11,000 volts and supplies a current of 750 amps. The total resistance of the power lines between the power station and the factory is 1.5 ohms. Calculate the output of the power station. So to find the power output, we just have to find the power, which is equals to IV. So it's going to be 750 times 11,000 volts. So 750 times 11,000. That would give us 8,250,000 watts. We can also write this in standard form, or we can just write it in number form. Part 2. The potential difference across 1.5 ohm of the power lines. So the current is going to be the same because it's a series circuit. So V equals to IR. So I is 750 and R is 1.5. So when we multiply them, we would get 1100 volts. Part 3. The power supplied to the factory. So to find the power supplied to the factory, first we have to find the voltage supplied to the factory, since power is equals to VI. So to find the voltage supplied to the power factory, we have the total voltage, which is 11,000, and then we have the voltage across the wire, which is going to be 1,100, rounded to the two significant figures. So we can do 11,000 minus 1,100. So when we do that, we would get 9,900 volts. So now to find the power, we have 9,900 volts times the current, which is going to be 750. So that would give us 7.4 million. 7.4 million times. So we can do times 10 to the power of 6 watts. We can write it as this. So our answer is going to be 7.4 times 10 to the power of 6 watts. That's going to be our answer. So that was the last question. I hope you have enjoyed the video and have learned something from it. So if you have enjoyed the video, make sure to like and subscribe for more upcoming content. And if you have any comments, questions, or suggestions, make sure to drop them down below in the comments. And thank you for watching.